Everybody, tonight we're trying to establish the minimum value of this trig expression in the interval 0 to the power 2. So that means x is strictly greater than 0, strictly less than pi over 2 radians. Okay, and it's common to use this interval notation in a calculus class, but we're going to prove, or we're going to find the minimum value of this expression without any calculus at all. No derivatives, no set derivative equal to 0 and all of that. We're just going to use something called the AMGM inequality. And you're going to see why this is important in just a minute, why actually sine 2x and tangent x are both positive in this range of numbers, okay, in this domain, this restricted domain. And the thing that's different about this problem than the senior problem just used integer constants, like I think this was 8 and this was 12. These are irrational constants, and so I want to show you that the processing in the algebra is quite similar. I've done most of the work for you, but here's the original inequality, and this is just kind of like some standard stuff. Oh yeah, we use the double angle sine. Sine of 2x is equal to 2 sine x cosine x. We use that here. That's all that happened right here. What else is going on? This part right here is just doing a common denominator. We multiplied this guy by sine x over sine x to get a common denominator. Now the next step's a little elusive, but the next step right here just exploits the fact that the well-known result of sine squared theta, the Pythagorean identity, sine squared theta, sine squared x plus cosine squared x. It's another name for the unit circle, really, in terms of the angle x. Okay, so this is equal to 1. And if you notice, that's exactly all we did. We turned this constant. This is kind of crazy. It's like you do it just because it makes the AMGM inequality result process a little easier. That's kind of unmotivating. It's hard to see that in advance. I really didn't know to do it. I just looked at the solution. But you see right here, we just multiplied root 7 by 1. Okay? But what that does, that leads to this nicer expression that we can work with. It's easier to use this expression on the AMGM side, and you'll see what I mean here in just a minute. I'll write down what the AMGM inequality states, and it's for positive or non-negative values. But if you have a plus b, which is called the arithmetic mean, okay, a plus b over 2 is the arithmetic mean. Add the two numbers up, divide by 2. That's greater than or equal to what is called the geometric mean, which is just the square root of the product of the two values. Okay? And I'll put a dot here, even though juxtaposition connotes multiplication anyway. I'll just write the dot. But notice, you see this red dot? I just put it there because this is the inequality. It's really fundamental. It relates addition and multiplication. Okay? To me, that's kind of interesting. And and again, that's why the 0 to the power over 2 is important, is because sine 2x, from trigonometry, sine 2x and tangent x are positive in this interval where they're defined. Tangent x is undefined, like what, at pi over 2, I guess. But it's strictly greater than 0, actually, in this interval of interest, okay? So anyway, all of this work is, this is what justifies this statement right here. And again, I will emphasize that for this inequality to work, we have to have both A and B. We have to have both A and B non-negative. Okay, greater than or equal to 0. And again, I've shown most of the work just so you won't have to watch me write it all down. But so here we go. This is our original, or this is the application of the AMGM inequality to our statement up here. This part right here. Now, so we divide by 2 right here, and this next step just is multiplying through by 2 to get the 4 right here. Okay, and then after that, it's fairly routine because this is true. This is also true, and this is our original expression, right? Okay, so we've completed. Remember, we started here, did the algebra, and got to this stage, and that's what this piece is right here. But we've shown that it's greater than or equal to 2 root 7. Okay, now notice that 2 root 7, if you want to get a feel for the size of that number, 2 root 7 is same as the square root of 28, right? But the square root of 28 is a little bit bigger than 5 since the square root of 25 is 5. So this is a number strictly greater than 5 right here. And I use some software, online software, and you can see right here, here is the graph. You have vertical asymptotes. This is probably happening at pi over 4, But you can see right here, it mins out at a number a little bit larger than 5, if you can see that. Okay, I couldn't make it much bigger to make it fit on the screen, But so anyway, but this is our answer. This is the answer to the problem. The minimum value is 2 root 7. You get a feel for the number. 2 times 2 is 4, and you take it inside the radical, and you get the square root of 28, which at least you can estimate that's a number between 5 and 6, which is where this thing bottoms out. Now again, we're just working in the interval 0 to pi over 2, which is what, like 1.5 something, So, but it is periodic, and it looks like a period of pi here maybe. I don't think it's 2 pi, but in any event, it's periodic. We were just working in the interval from 0 to pi over 2 though, and this would be that little spot where it's as small as it can be. Again, square root of 28. So that does it, folks. Let's write that down. That minimum value is the square root of 28. And last word on it is that these SMO problems typically are using integers just for computational ease, but really the irrational numbers don't impose that much of a difficulty. The main idea is to use this Pythagorean identity to rewrite the square root of 7 in kind of this cumbersome way to make it more amenable to the AM-GM inequality. Alrighty, that's all for tonight.